Hi, welcome to the fifth and final part of our module on radiation detection. In the first four parts, we have introduced the different classifications of detectors and factors affecting detection. We also gave some examples and functions of gas field detector, solid state detectors, and those that rely on chemical and nuclear reactions. We are now on the part of collecting these charges generated in the detectors and perform signal processing using a standard nuclear instrumentation system. Here, I would like to show you the chart of principle of radiation measurement for quick guide and recap of the past discussions. In here, the types of radiation are classified according to charged particles alpha and beta, photons, X-rays, and gamma rays, and neutral particles neutron. So the radiation interactions are direct ionization for charged particles, production of secondary electron via photoelectric Compton pair production, and then for neutron, production of charged particles by nuclear reaction. So the different radiation detectors in here are gas field detectors, semiconductor and scintillation, which is classified as solid state detector, and other types of detector not mentioned here, which are luminescence detectors and activation detectors. So for the gas field, the ionization can cause current or voltage signals, whereas in semiconductor and other types of solids, you have this excitation, production of light signal, and processed by the photomultiplier tube. All these charges generated by the ionization in the gas or excitation in solid-state detectors and in photomultiplier tube produce current or voltage signals that will be processed by an electronic system or device. The electronic system will then give out display output in current meter or as counts or as a spectrum. So these main components of processing system will be shown in this module. So the stages of radiation detection. So this diagram shows the stages of radiation detection. So in here, the radiation interacts with the transducer, depositing energy by excitation or ionization of the transducer atoms. The transducer is physically coupled to an electronics stage, where the subtle effect within the transducer is converted into a measurable electronic signal. The output from the electronic signal or stage is fed into a display or storage device for interpretation. So this is the standard nuclear instrumentation chain. We have our source, radiation source that carries energy. We have a detector that we have been discussing. We have a supply bias to collect the charges, the preamplifier, the amplifier, the SCA or single channel analyzer, the MCA or multi-channel analyzer. The SCA will give us linear pulse counted by a scalar rate meter. The MCA will be connected to a computer which will give us the spectrum. Here, the preamp pulse will give us a linear pulse. The amplifier gives us an amplified linear pulse, while the SCA will give us a logic pulse. We will discuss them each one by one. And in actuality, these are the parts of the nuclear instrumentation chain that we have in PNRI, particularly in applied physics research section. So we have here a radiation source. This is iron 55 and a proportional counter. The detector is a proportional counter applying the bias. This is our high voltage supply. This is our preamplifier. This is our preamplifier. And then we connect this preamplifier is then connected to an amplifier. The amplifier is either connected to an SCA or to a multi-channel analyzer. Let's see them one by one. So this nuclear instrumentation bin, or we shortly call it the NIM bin, is the power source and holder of the modules. This are what we call the modules. All of these gets their power from the nuclear instrumentation chain, and this volts indicates the voltages supplied to these modules. All, but one do not get their power from the nuclear instrumentation module. So which do you think among these modules do not get their power from the nuclear instrumentation module that ranges from 24 to negative 24 volts? So next we have the preamplifier, particularly for a proportional counter. The purpose of the preamplifier is to provide an interface between the detector and the signal processing electronics. There are types of um, preamplifiers. Some are voltage sensitive, some are current sensitive. For a voltage sensitive preamplifier, it provides a pulse with voltage equal to V max equal to Q over C, where Q is the charge collected and C is the capacitor or capacitance of our preamplifier. So the linear pulse gives us the rise time and decay time. What are these? So in terms of electronics, the rise time gives us the time wherein all the charges are collected by the preamplifier, whereas the decay time is the time where that the capacitor is being discharged. And this can be seen, this linear pulse, preamplifier linear pulse can be observed in an oscilloscope. This one on the left side is a pulse coming from an amplified signal. So an oscilloscope is used to view signal pulses versus time. The three basic viewing functions of the oscilloscope, that is the vertical adjustment to allow you to view or to vary the signal amplitude, the horizontal adjustment for the time, and the trigger, which allows you to select a specific pulse to focus on. So here are the instrumentation modules. First off, we have the high voltage bias supply. This supplies a high voltage to the detector only and provides bias for charge collection. The second module is our amplifier, which amplifies the preamp signal or the linear pulse. So since the preamp signals are too small, and once you process the signal, we go through many electronics, this preamp pulse will eventually die down. So we need to immediately connect the preamp pulse to an amplifier to amplify the pulse for further processing. So the amplifier has three main functions. First is to extract the pulse height information from preamp pulse by shaping, and then reduces the noise for smoother pulse appearance or pulse or noise filtering. And then, of course, by the name itself, amplification. So in here, we have the left image is your preamplifier pulse, which is very small, that needs to be amplified using this amplifier with this amplifier gain setting. Next, the third module is our amplifier coupled to a single channel analyzer. So this single channel analyzer gives out the signal if the input is within the set value. The output is in the form of a logic pulse. The value called window in here is determined by setting a lower level discriminator or LLD and an upper level discriminator ULD such that the delta E or the window is equal to the ULD minus LLD. In some systems, the window can be set instead of the ULD. So for this image, the single channel analyzer has set an LLD and ULD, H1 of H2. The logic pulse will register. What do you think? How many pulses will be registered? So here, the registered pulse or the registered logic pulse will be counted by our scalar rate meter. So they are used to count the logic pulses given out by the SCA for every given counting time. The small screen can give out the counted pulse and or the counting time. So for this example, if we have set the LLD and ULD at this window, how many counts would you think we will see in our counter or scaler? Yes, that would be 2 counts. So this image on our left is a linear pulse and a logic pulse as shown in an oscilloscope. So a linear pulse carries information through its amplitude and shape, whereas a logic pulse has a standard size and shape that only tells us the presence or absence of a pulse with a set pulse height. So the functions of amplifier, we have there the fine gain or the fine small amplification of the linear pulse from the preamplifier. We have the coarse gain or big multiplication factor or huge amplification of the preamp pulse as shown here. So the coarse gain about 4, 8, 16 magnitudes, whereas in fine gain is in decimal places. And then you have the shaping time in terms of microseconds from zero point 0.5 to 10 microseconds and pole zero adjustment. So the pulse amplification is controlled by these two, the fine gain and coarse gain. The pulse shaping is controlled by this shaping time, and the noise reduction is both the shaping time and pole zero adjustments. The full width at half maximum of the spectrum peak depends on the shaping time. In particular, a shaping spectroscopy amplifier needs to integrate a fast rise and slow fall signal over the longest possible time to attain the best possible resolution, such that the user needs to choose a compromise between event rate and resolution. So short shaping time does not include all of the preamplifier pulse, but less signal, and a long shaping time includes too much signal noise, but lesser resolution. So here, longer shaping time means better peak resolution, but has larger dead times. The single channel analyzer, or SCA, sets the threshold for the system to generate a logic pulse. It gives out the signal if the input is within the set value. For example, here, the set value is delta E, and which two logic pulses were generated. A single channel pulse height analysis consolidates the number of logic pulses counted over a range of pulse values or pulse heights. The range of pulse heights is obtained by adjusting this LLD or LT and ULD of the SCA to scan through all the ranges of pulse heights. Whereas in an MCA or multi-channel analyzer, it works like many SCAs in a row, analyzing data one after another. It already converts the signals to the analog to digital converter, which stores outputs into a defined number of channels. So the analog to digital converter converts pulses or analog signal into a digital data, which stores outputs into a defined number of channels. The basic function of an ADC is to produce a digital code or number as its output that is proportional to an analog voltage supplied to its input. In general type of ADC, conversions are carried out continuously at a fixed clock frequency. Like for example, a 100 megahertz clock will produce 10 megasamples per second, or equivalently, that's one sample every 10 nanoseconds. In an ideal ADC, each conversion of input voltage to output code is independent and perfectly linear and occurs instantly. Again, this is for an ideal ADC. So in summary, this module, we have discussed the detection of radiation. So in summary, detection of radiation is based on the measurement of ionization or excitation in solids, liquids, and gases, the changes in the properties of the materials, and nuclear reactions producing charged particles and photons. The general properties of radiation detectors include energy resolution, efficiency, sensitivity, and resolving time. Other factors affecting radiation are the types of incident radiation, its intensity and energy, and the application. Will it be used for dose rate, spectroscopy, intensity, or contamination measurement? The types of radiation detectors that were discussed are gas field detectors, ionization, proportional counter, and Geiger-Müller counters. We have the solid-state detectors that are further classified into semiconductor, scintillation, or luminescence detectors, and detectors that rely on chemical changes and activation by neutrons. And here, this chart will give us a guide on how these charged particles, photons, and neutrons are processed in the different detectors, yielding a display either a current meter, a count number, or a spectrum. And here is a table of the overall summary of the types of detectors, the radiation detected, their typical use, and special features. These are the references that I used: the instructor training program lecture materials, PNRI nuclear training lecture materials, and all these textbooks. So this is the end of our module on radiation detection. Hope you enjoyed and learned something new and enjoyed learning as much as I did. Thank you.